Module 10, Flight Control Systems. Now, for Chapter 10, let's start at first with the overview of the flight control system. Flight control systems enable the pilot or automatic systems to control the aircraft's attitude, okay, pitch up and down, roll right and left, trajectory, meaning the heading, and aerodynamic performance, meaning how much lift, drag, deceleration, acceleration, stall, etc. These systems manipulate airflow and the stall aversion rather. These systems manipulate airflow over control surfaces. These are the control surfaces. And the controls are the ailerons, elevators, rudder. Okay, the control surfaces are the wings and stabilizer. Also the fuselage. Okay, so these systems manipulate airflow over control surfaces to generate moments about the aircraft's axis to enable the roll and change of direction or up and down pitching. Aircraft motion is described about three principal axes. You have the longitudinal axis, which is for the roll. This is the longitudinal axis for the roll, right and left. Lateral axis, which is this axis here for, this is the lateral axis, okay, for the pitch up and down. And finally, vertical axis for the yaw or the rudder, which moves the airplane to the right. It can do it without turning via the rudder, okay? Although the rudder is also used to perform an efficient roll maneuver. So longitudinal axis, which is crossing longitudinally the aircraft, and it is where the roll action takes place, okay? Lateral axis, which is about the wings, it is for pitch up and down, rotation. And vertical axis, like going in the middle of the aircraft, is for the yaw, rudder yaw, for right and left yaw motion. Control effectiveness depends on aerodynamic forces generated by control surfaces, surface deflection, airspeed, and surface area. Another note is that the elevator, when it moves upwards, okay, it is for the pitch, by the way. So when it's rotated upwards, the air would push against it and it would push the tail downward, rotating the nose of the aircraft up, okay? So in order to pitch up, the elevator should go up so that the air would push the tail down and the aircraft would turn upwards. Meanwhile, or on the other hand, if the elevator goes down, then the air would push against it upwards. So the tail would be pushed upwards and the aircraft would pitch downwards. As for the rudder, when it goes to the right, the tail is pushed to the left and the entire aircraft, the tail would be pushed sideways here and the aircraft would go to the right. But when the rudder goes to the left, so the air would push the tail to the left, okay, and the entire aircraft would be pointing to the left as well. Now, again, another explanation to break it down more simply how the elevator works. So imagine this being the elevator, okay, this part here. So when the elevator is up, the air would push it like this downwards, so the nose of the airplane would go up. All right. Meanwhile, if the elevator goes down, so the air would push it upwards, it would push the tail upwards, so the aircraft itself would go downwards. It would be pitching down. Primary flight controls. Primary flight controls are essential for maneuvering the aircraft in all phases of flight. So what are these? At first, you have the ailerons on these two sides that are responsible for rolling the airplane to the right or to the left. You have the right wing, the left wing. Okay, you have the elevators that are responsible for pitching up and down the aircraft, and the rudder, which is part of the moving part of the vertical stabilizer that would yaw the airplane. It would like turn it right and left, not roll it. It would turn its heading right and left. Along, of course, when you're turning, you should be using both the aileron and the rudder so as to reduce the strain and the air pressure on the rudder alone. Okay, so you should not be using just the rudder. The rudder is usually used for heading correction during landing and during takeoff, and the horizontal stabilizer that is housing the two elevators. Now, starting with the ailerons. Ailerons are hinged control surfaces located near the trailing edge of the wings. Here and here, these are the ailerons. They control roll by producing differential lift between the left and right wings. Okay, so one goes down, the other goes up. So the air would push this one, okay, upward, and this part downward, so it would draw to the left, and vice versa. Now, the lift generated by a wing is given by L, which is the lift force, is equal to 1/2 rho v square SCL. S is the surface of the wing, CL is the lift coefficient, V is the velocity of the moving air, the airflow velocity, and rho is the density. Now, aileron deflection alters the lift coefficient, CL, producing a rolling moment. The moment of rho, m rho, is equal to delta L, okay, the difference or the shift of the lift force, because as you roll, the lift power decreases, okay? It actually turns into two components. Horizontal component that like aids the aircraft to roll, to turn, and the vertical component that is actually would be the lift itself, okay? So m rho is equal to delta L times b, where b is the wingspan. Wingspan is this distance over here from the trailing, from the leading edge to the trailing edge. Now let's explain a little bit on how does the lift force change, okay, and what causes it to change. You see, when we spoke about the moment of rolling is equal to delta L multiplied by B, okay? Why do we have a difference of lift? And what is B? At first, B is the wingspan, which is the distance from one tip of the wing to the tip of the other wing. That is the B value, okay? Or wingspan of the wing. Now, delta L. Imagine the aircraft flying in a leveled flight, meaning it is horizontal, okay, flying parallel to the horizon with no roll, no banking. That would be the leveled flight, okay? So without any roll, and actually, yeah, when we talk about leveled flight, we talk about it's not ascending or descending. No, what I mean here is that it's flying with 0 degrees angle. So what you have is the entire lift force would be vertical, but at the same time it is always 90 degrees to the wing itself. That would be the lift force. So this force is always forming 90 degrees with the wing, and it is absolutely vertical. Meanwhile, during a roll or a turn, what happens is that this wing, okay, would be turning, let's say, 30 degrees or 40 degrees, whatever. So that angle would cause the level, okay, of or like the orientation of the lift vector to change. Now, the lift vector is always 90 degrees to the wing. However, it's no longer generating lift completely. It becomes broken down or divided into two different components. The LH, which is the horizontal component that would start like assisting, it will assist the aircraft during the motion of rolling during the turn, and the vertical component, which is the vertical part of the force that is actually generating lift. So in other words, you see, LV would be much smaller than L, Why? Because the lift force, what used to be pulling completely the airplane, is now broken down into two components. One component is LH, which is pushing the aircraft sideways and assisting with the roll maneuver, and LV, which is actually generating lift. So the differential between lift during a leveled flight and lift during a roll, so L minus LV, so to speak, multiplied by the wingspan, which is the distance from one tip of the first wing to the tip of the second wing, okay, that would give us the rolling moment of the aircraft. Elevator. Elevator is mounted on the horizontal stabilizer. That is the horizontal stabilizer. And the deflection of the elevator changes the tail force, which means it creates a pitch up or pitch down moment. So creating a pitching moment about the center of gravity, okay, of the aircraft. So the pitching moment is expressed as the moment of pitch is equal to the force exerted at the tail multiplied by the distance from the tail to the center of gravity, okay? L is the moment arm between the tail and the center of gravity of the aircraft. So to visualize it graphically, when you have the elevator pulled up, what happens is that the force would push the elevator down, okay? That would create a moment that is equal to F, or force exerted against the tail, multiplied by L. L is the distance between this line, okay, at the elevator and the center of gravity of the aircraft, which would be somewhere here, okay? Actually, it would be at the front, okay? Close to the engine because the other parts are not so much heavy. So L would be somewhere here. That would be the L distance. Multiplied by F, the force exerted against the tail, this would give you the moment of the pitch. So where L is the moment arm between the tail and center of gravity. And by the way, in such case, it will pitch up. If the elevators are turned in the other direction, the air would push the tail up, so the aircraft itself would pitch downward. 10-3, the rudder. The rudder is attached to the vertical stabilizer, this part here, which is the vertical part of the tail, and controls yaw, which is the right or left-sided movement, okay? The left or right push against the aircraft. The rudder deflection produces a lateral force going this way and this way, not a roll, that generates a yawing moment, like actually the rudder of the ship. The moment of yaw is equal to the force pushed at the side of the rudder, okay, multiplied by LV, which is again the vertical tail moment arm. The moment arm is actually this length here going all the way from the vertical elevator at the side, like at the point of the rudder, the connection of the rudder, all the way to the front of the aircraft. This distance is the arm of the moment that's being generated. 10.3, secondary flight controls. Secondary flight controls enhance performance and handling but are not required for basic control. Let's start with the flaps. Flaps increase wing camber, which is the wing curvature, as you see here. They are extended, and surface area, which allows higher lift force at lower speeds. Maximum lift coefficient increases with flap deflection. Okay, so the lift coefficient would be CL0, which is before the deflection or the extension of the flaps. That was like the original lift coefficient of the wing, plus delta CL, which is the lift coefficient due to or the lift coefficient change due to flap extension. This reduces stall speed, okay, which is the speed at which a wing on an aircraft can no longer produce lift. So, in other words, this allows the aircraft to generate lift even at lower airspeeds. So, V stall, or the velocity of the stall, is equal to square root of 2W, which is like the width of the wing from leading to trailing edge, I believe, divided by rho S CL max. Exactly. Rho being the density of the air times S, which is the wing section, multiplied by the maximum lift coefficient, which is the CL0, or the original lift coefficient, with the added lift coefficient that has been uh, accounted for after the extension of the flap. 10.3.2 slats. Just like the flaps, the slats extend except from the leading edge of the wing instead of the trailing edge. And like Airbus has both of them, the slats and the flaps. Okay, so they extend from the leading edge to delay flow separation and increase stall angle of attack. So it means that they allow the aircraft to increase the angle of attack against the air, okay, without stalling, where it can stall on lower angles when the slats are not extended. And by the way, slats and flaps are usually extended during takeoff and landing. So they improve low speed handling and reduce stall severity. During takeoff, both flaps and slats are extended in case they both exist on an aircraft. Okay, some aircrafts only have flaps without the slats, so they extend in order to provide more lift to the aircraft at lower airspeeds, allowing it to take off and to lift off from the ground at lower airflow velocities. Okay, and this would allow the aircraft to actually separate from the ground and fly off. Meanwhile, and of course, there is a drawback, which is an increased drag, but you don't mind having an increased drag during takeoff. Meanwhile, in landing, the slats and flaps are extended in order to increase the drag intentionally in order to slow the aircraft down, but at the same time, it uses some part, like a part of the airflow, in order to generate lift and lower the descent rate so that the touchdown would be smooth. So two objectives would be accomplished in such case. These are slowing down the aircraft, so reducing the airspeed by increasing drag, while at the same time reducing the descent rate, or the VSI, so as to enable the aircraft to touch down at lower descent rate and lower velocities. 10.3.3 Trim systems. Trim systems relieve continuous control forces by adjusting the neutral position of control surfaces. Okay, these are the trims, like a small part of the rudder of the elevator that is controllable. Like these are trimmed, these are placed down or up in order to release the burden of continuously controlling the yoke by the pilot or even the autopilot. Trim changes the equilibrium condition without altering aircraft attitude directly. 10.4 Mechanical, hydraulic, and fly-by-wire controls. Okay, 10.4.1 Mechanical control systems. These systems use cables, rods, and pulleys to transmit pilot input directly to control surfaces, meaning that the same force that the pilot is applying to a control, that same force, that very force, is being transmitted to the wing control to move it. So the pilot is directly moving the rudder or the aileron or or the levels, okay, the elevators. They are simple and provide direct tactile feedback, but become impractical for large aircraft. Why? Because they would require much higher control forces. Then for two, hydraulic control systems. Hydraulic systems use pressurized fluid to move control surfaces. Significantly, they reduce pilot effort. Why? Because it's no longer required to have the exact force exerted by the pilot himself in order to move these controls. So they use pressurized fluid and hydraulic systems to relieve the pilot from being strained and from applying force in order to move controls. Control force is given by F equal P multiplied by A, where P is the hydraulic pressure and A is the actuator piston area. Now, hydraulic controls allow large high-speed aircraft to be maneuvered efficiently. 10-4-3 fly-by-wire systems, or FBW. These systems replace mechanical linkages with electronic signal transmission. The pilot inputs are converted into electrical signals that are then processed by flight control computers, then sent to actuators. What the actuators does, by the way, is that the same signal that has been transmitted, okay, by the command, it would be analogous to the same action, mechanical action, executed by the pilot. So when he moves the handle, the very same movement should be replicated by the actuator, which receives a higher amplitude current, but the current would be the same value, like the same analogous signal, mechanical signal, okay, mechanical variation. The actuator would be moving the control surface. Actuators, by the way, convert electrical signal into a mechanical signal, okay, into a mechanical electrical energy into mechanical energy, and the actuator itself would be controlling the surface instead of the pilot directly. So the pilot signal would be processed by the computer as an electronic signal and then replicated to the actuator with the same frequency and the same, like it needs to mimic perfectly the action of the pilot himself, except it should be amplified, okay, so as to be capable to move the actuator. Now, the control laws ensure stability and envelope protection. The control command can be expressed as delta equal K multiplied by U, where delta is the surface deflection and U is the pilot input. They should be proportional. FBW systems allow automatic trimming, load alleviation from the pilot, okay, relieving the pilot from burden, and fault-tolerant operation. Then 5, control surface position indication. Control surface position indication systems provide feedback on the actual position of different controls. This is very necessary, especially like, for example, during control check, where the pilot would check if the controls are responding correctly to his own input, okay, before verifying the airworthiness of the aircraft at that moment, before like taking off. This is a part of the checklist before takeoff. Sensors such as potentiometers, resolvers, or linear variable differential transformers, LVDTs, are used, okay? Sensor output voltage is proportional to surface displacement. So in other words, when the surface changes, okay, when it is displaced, it creates or changes or alters, like it creates a current. So when, for example, this air brake, this spoiler here moves upward, its own rotation would generate a current, okay? Why? Because it is like connected to an LVDT or variable differential transformer, okay, potentiometer, which means it would change the resistance value, or resolvers, etc. Different types of sensors that would be detected in the cockpit, and it would be processed and analyzed to get the significance or like the actual value of the angle in respect of the value of the current or the alteration of the current when we're talking about a potentiometer, which changes the resistance value, okay? So, or the voltage value being collected, okay? So that when the resistance changes, the value of voltage being detected would change. That would be like processed and analyzed to understand the current angle of deflection for whether the spoilers, whether the flaps, or like the rudders, the ailerons, all of these controls. Sensor output voltage is proportional to surface displacement, which is V equal, exactly, it is based on the voltage change. V is equal to K multiplied by X, where X is the surface position. Accurate position indication is essential for monitoring system health and detecting asymmetry, whether like one elevator is moving further than the other elevator, although, yeah, like one is moving more than the other, or the ailerons, which are very necessary for the role, indispensable for the role. One is moving erratically in respect to the other. So this is important so as to ensure safe operation, especially in hydraulically or electronically controlled aircraft. Operational awareness and limitations. Understanding flight control system architecture allows pilots and engineers to recognize abnormal behavior, anticipate failure modes, and apply correct procedures. Modern aircraft relies on layered redundancy, which is necessary and important to ensure that in case you had a failure, another system would back you up and to guarantee a continued controllability under all operating conditions.